All right, this is going to be the third video for chapter 14. This is going to be covering the last 3 sections of the chapter. Okay, so we're going to talk now about waves interacting with one another. So let's say that I have y1, so this has a certain amplitude, and this is going to interact with another wave that is a bigger amplitude. So we can see that this is one wave, this would be the other wave, and so we could say like this one was traveling this way and this was coming from this end and it's traveling this one. According to the law of superposition, when those waves meet, they're going to produce a wave with a much larger amplitude. So in other words, this would be y1 and y2 added together. And then once those meet in the middle, they're going to go on their merry ways like they never even met. So this one that was traveling left continues to go left. The one that was traveling right continues to go right. Now this is called constructive interference because it adds up and constructs a bigger wave. Now if the pulses have opposite amplitudes, meaning one is a positive amplitude and the other is a negative amplitude, it's still the law of superposition, so that means when they add, their amplitudes add together. Well, if this was like a +2 amplitude and this was a -2 amplitude, when they meet in the middle, they would cancel each other out. And then once they meet in the middle, they're going to continue on their merry ways and nothing ever happens to those waves. So it's just the moment when they meet, their pulses will combine. Now in this case, it destroyed the amplitude. So this is destructive interference because it results in a smaller amplitude. So constructive results in a larger amplitude. Destructive results in a smaller amplitude because it doesn't necessarily always cancel each other out. If we had a +3 and a -2, they would meet here and we'd have just one with an amplitude of 1. Alright, this also occurs if I have 2-dimensional waves. So these could be like water waves that were interacting with each other. So if I have a drip of water here at this first place and I have a drip of water here at this other one, when those waves meet, they're also going to combine. So we're going to have some constructive interference going on here where I have 2 crests meeting, and then where I have crest and trough meeting, it's going to result in destructive interference. And I don't know if you can see these lines that are kind of in here. It looks like you kind of took an eraser and went through this place. Those are called nodal lines, and we're going to see that in the middle in a little bit. So those are nodal lines, and that's caused by destructive interference where the 2 are canceling each other out. Alright, so anytime I have 2 crests meet, that's our constructive interference. Anytime I have a crest and a trough meet, that's going to be my destructive interference. Okay, a standing wave looks like it's not moving. So if I were to take a rope and we were going to make a jump rope out of it, then it's either going to be at the top or the bottom, but it looks as if this doesn't really move. I don't see a wave actually going through here. It just is either up or down. And that's what's called a standing wave because it doesn't really appear like you can see the wave going through it. It just appears to stand in place and oscillate back and forth. And these are found in all kinds of musical instruments and any kind of columns of air. Now, for this particular wave that we have on this string, I am showing here half of a wavelength, because if I look at a transverse wave, an entire wavelength is like from crest to crest, or here beginning to beginning. So if that's an entire wavelength, what I see on here is just half of a wavelength. So that means I'm only fitting half of a wavelength on here. So in order to fit a whole wavelength, I'd have to have twice the length of the rope. Okay, now the places where it's fixed on the ends are called nodes. They don't move. And the antinodes are the places where it moves. So this one has twice the frequency, because notice I'm going to have 2 antinodes instead of just 1, and now I have 3 nodes. This one, this final wave over here, part C, This has 3 times the frequency of this first one. This first one we call the fundamental frequency. This one would be 3 times the fundamental because it has 3 antinodes. So the number of antinodes tells me the harmonic. So since this has 3 antinodes, this would be the 3rd harmonic. This has 2 antinodes, so this would be the 2nd harmonic. This one is what's called the fundamental. And the frequency of the 2nd harmonic is twice the frequency of the fundamental. The frequency of the 3rd harmonic would be 3 times the fundamental. Okay, so that lowest frequency is the fundamental. All the other higher frequencies are harmonics. So 2nd, 3rd, 4th, 5th, 6th, and so on. And we said that for our fundamental, if we go back here, that it was going to take, for one wavelength, it was going to have to be 2 times the length of my rope, since this is only half of a wavelength. So if I want to find my wavelength for the fundamental, it is 2 times the length of the rope. And since velocity is frequency times wavelength, then that means my frequency would be the velocity divided by 2 times the length of the rope. Now, if it's a harmonic, I can make this, my wavelength is 2L divided by the harmonic. So if this was the 3rd harmonic, then the wavelength would be 2L divided by the harmonic, which would be 3. And my frequency then would be 3 times whatever that fundamental frequency was. We'll call it F1. So the frequency of, let's say, the 3rd harmonic would be 3 times the fundamental frequency. And then we know that the wavelength is 2L divided by the harmonic. So if I had like the 7th harmonic, the wavelength is always 2L divided by the harmonic, in this case 7. And then the frequency of the 7th harmonic would be 7 times the fundamental frequency. Okay, so there's going to be 2 basic equations that we're going to be using to solve standing wave problems. We're going to have the wavelength, 2L divided by the harmonic, and we're going to know that the frequency is whatever that harmonic is times the fundamental. Okay, if we talked about stringed instruments are just what we've been looking at as far as harmonics. So in a guitar, each one of the strings has the same length, but they vary in their density, which means that the frequencies are different. Okay, on a piano, they have not only different densities, but they also have different lengths. And the cabinet itself, since it's made out of wood, acts as a sounding box, and a sounding box helps to amplify the sound. And if we want to tune a piano, we can change the tension in those strings. Okay, standing waves also occur in columns of air. So in this case, I can have like a Coke bottle or a pop bottle here, and if I blow across the top, that creates an antinode at the top and a node at the bottom. Okay, and all of your woodwind instruments act like this. So we're going to have a node here and an antinode here. And this shows you, I suppose I could draw a picture here. So here's my node, and then I would have my antinode at the other end, like that. Okay, if both ends are open, then I'm going to have an antinode at both ends. And in this case, all the harmonics are possible. So the 1st, the 2nd harmonic, the 3rd, the 4th, the 5th, all of them are possible. And these are going to work just like strings. So in other words, we're going to be using wavelength is 2L divided by the harmonic. However, if we go to where one end is open and the other one is closed, so this was like my pop bottle that I had and I drew in there. In this case, this is only going to be half of a wave, or this is only going to be a fourth of the wavelength. Because if this is one entire wavelength, what's being shown over here is only this much. So this is only a fourth of the whole wave. So this is 1/4 of the wavelength, which means the wavelength is going to be 4 times the length for my fundamental. And if I wanted to go to any harmonic, it's 4L divided by the harmonic. So for pipes that are open on both ends, or for strings, it was 2L divided by the harmonic. If it is one end open, one end closed, then I'm going to do 4L divided by the harmonic. Now, because I have an antinode at this end, I don't get all of the harmonics, because I don't have one where I'm going to have a node at one end and a node at the other. So I'm only going to get odd harmonics. So I get the fundamental. I do not get the second harmonic, but I would get the third harmonic and the fifth harmonic. So here we have an example. This is using standing waves. So they're giving me that the fundamental wavelength is 0.88. They asked me to find the length of the bottle and the frequency of the third harmonic. So I know since it's an open bottle, it's 4L divided by the harmonic, because it's open on one end and closed on the other. Since it's the first harmonic, the fundamental, I just put in 1. So I took 0.88 divided by 4, and my length is 0.22 meters. Now to find the frequency, I need to first find the frequency of the fundamental. So velocity is frequency times wavelength, and we're talking about air and sound, so that is that 343 number. Frequency times the wavelength that I was given. So the frequency of the fundamental is 389.8 hertz. The frequency of the third harmonic is 3 times that fundamental. So I took 3 times the fundamental, and that gets me 1200 hertz. Okay, beats are also caused by constructive and destructive interference. So if I have 2 notes played by 2 clarinets and they're out of tune, they're going to be close in frequency, but they're not going to be the same. So that means I'm going to have areas where I have destructive interference and the amplitudes cancel out, or I'm going to have areas of constructive interference where I get larger amplitudes. So that creates this beat pattern that I see here. And if I want to find what's called the beat frequency, that's the difference in the frequencies of the 2 notes. So in this example, I have a tuning fork of 261 hertz, and I'm trying to tune a piano, so I hit a key on the piano. And I hear a beat frequency of 3 beats per second, or in other words, 3 hertz. So that means they ask me to find out what's the possible frequency of the piano key. Well, since I'm hearing 3 beats, that's either 3 beats above this, so 3 hertz above this, or 3 hertz below this. So 261 plus 3 gets me 264 hertz, or the other possible frequency would be 261 minus 3, which is 258 hertz. All right, that finishes chapter 14.